Hi guys, and welcome to my channel. Today I'm going to go over a couple of signal lines on the Coco cartridge port that I just figured out really how they work, and so I wanted to share that with you guys, make a video of it, and hopefully this helps someone in the future. A few years ago I was trying to build a multi-pack interface. I was just playing with the idea and looking at the diagrams and all the information for the Coco. It's pretty obvious what 80% of the lines on the cartridge slot do. However, there's a couple lines, the SCS, the CTS, and the SLENB line that aren't very well described in the manuals, and I couldn't quite figure out how exactly they functioned. I mean, the descriptions were there, I could understand kind of the area where they were working, but I didn't know how they actually worked. Now, a couple of weeks ago, I was listening to the Coco Crew podcast, and I was listening to John Linville talk about some technical aspects of the Coco, and he gave me the hint that made me understand exactly how these lines work on the Coco. So I wanted to share that with you guys. I hope you enjoy it. Here's the pinouts for the cartridge slot. It's all pretty self-explanatory. The data lines are here, data 0 through data 7. Then we've got 16 address lines, which are showing what address on the bus is being accessed. And then there's a couple of lines that don't make much sense. So CTS, cartridge select signal. Does this mean we can select more than one cartridge, or is it just for one cartridge? It's very confusing to know what exactly that means. And then SCS, spare select signal. Spare what, for starters? And then again, it's a select signal. What does that all mean? And then lastly, SLENB, input to disable device selection. Now that one is okay, what does that mean? Does that disable these devices or other devices or the device you plugged in? Who knows? So I'm going to go back a little bit in the manual here and take a look at the descriptions for those signals. And CTS star, technically, this is the cartridge select signal. It is valid when the processor reads any location from C00 hex to DFFF hex, as long as the ACVC, this is also known as the gimme chip, is in map type 0, whatever that means. Note that it is not active while writing to these locations. Okay, so that basically, if I understood the context of this and a lot of the background, that probably would make total sense to me. But because I didn't, it didn't make any sense at all. I mean, they're just words. They're all in English, but combined together, and they just don't make any sense together. So it's very confusing when I was reading that. Likewise, SCS is described as the second chip select signal from IC9. Second chip, I don't know what, there's another chip or something. What is IC9? Who knows? It is active for both reads and writes to addresses FF40 through FF5H. Now, this bit of information is interesting because I know those are the hardware ports for external devices that are plugged into the system. So that gave me a hint. Okay, well, it's about hardware something or other. And this is active regardless of the map type. SLENB is described as this signal disables the internal device selection. This allows decoded but unused sections of memory to be used by the cartridge hardware, which sounds fascinating, sounds really cool, but doesn't really tell me how I could work with that. I'm going to try to explain what these signals do. Essentially, any digital logic chip has an enable line on it. And what that does is that the chip can be sitting in circuit, it's powered up, it's connected to everything, but unless the enable line is active, the chip just sits there idly. It doesn't, involve itself with what's going on in the rest of the circuit. So your ROM chips that are in a ROM pack, or the circuits within a disk controller or an Orchestra 90 pack or whatever, they sit in circuit, but they're idle until their enable lines go to active, and then they start communicating with the bus of the computer, which allows them to send messages essentially to the CPU, whatever. The challenge is that these enable lines, from the computer perspective, they need to only be enabled when the computer's accessing specific memory locations or specific addresses. In order to do this, you need to do something called address decoding. To do address decoding, what you would do is you take your 16 data lines that are coming in from the CPU, and you'd use a series of digital logic chips, so AND gates, OR gates, XOR gates, in order to create a mapping between the 16 input lines for the particular address that you wanted to one output line, which you would connect into your chip to enable it. Now, if you had to do that for every single device, you might end up needing like 4 or 5 chips just to do address decoding. And if you have to put that on every single, cheap ROM pack that you're trying to sell software on, it's going to add a lot to your cost as a manufacturer. As well, any other ROM pack device like a disk controller, if you have to add, 4 or 5 chips just to decode the address lines, it's going to significantly add to your cost. So these lines, what they do is they basically decode 2 of the most important address areas, and they decode them to a single signal, so that if you're plugging in a device into the computer, they can just use those 2 signals in some cases. They don't have to do any more address decoding, and they know they're active. So the cartridge select signal, for example, it's mapped from C00 to DFFF. Now this is where the ROM chip from a cartridge fits in memory. So if the processor is reading these memory locations, what happens is this signal goes active. It goes active low because there's a little star there. And that enables the chip on the ROM cartridge to turn on, essentially. And whatever data is in the ROM cartridge appears on the bus that can be accessed by the CPU. Likewise, SCS is a smaller range. It's FF40 through FF5H. These are your hardware ports for inputting and outputting control and inputting and outputting data from hardware devices. And so basically, if this SCS line goes, it means the CPU is trying to read or write to hardware within these ranges. And you may be able to just get by with just using SCS. Say, for example, if you didn't really care if it was, it could be any address in this range. And I think that's the way the disk controller works, is it just reads FF40 SCS and just assumes it's all good and starts answering. But what you can do is you can add additional logic chips and gates, OR gates, etc., in order to narrow down the range that you want to listen to. So if you wanted to listen to, FF60, you would use SCS combined with a couple of digital logic chips on the address bus to narrow the signal down to like FF60, and away you go. You can start answering whenever the CPU calls you. So that's basically it. They're basically, cheaters that allow you as a hardware developer to reduce your chip count, significantly when you're building devices. This last one, SLENB, is a little bit more interesting, and I'm going to describe this in a bit. But basically what this does is this allows you to create a device that can essentially take over the whole computer, because it will turn off all the all the device selection for everything in the computer, and it makes your device the one device that can do things. So, you could use this, I guess, potentially for like a direct memory access disk controller, or, if you wanted to create a new video card, you could use this. All sorts of stuff where you really want to take control of the whole machine, you use SLENB. I don't know of any devices that actually use this, but then again, I don't have a lot of devices in my collection. I really just have disk controllers and a couple cartridges and stuff. So Who knows? It would be great if you know devices that use the SLENB line. It would be great to hear about them because it would be interesting to know what uses them or what used them in the Coco. Thank you very much, Ty Sopko, for creating the schematic. I've used it like hundreds of hours. It's given me limitless entertainment, which I guess you got to be pretty nerdy to be entertained by a schematic diagram. But thank you again. You know, this is great that you created this. Anyways, here on this side we have the gimme chip. So let's mark that. Gimme. And the gimme chip has 3 lines, S0 through S2. Those go into a 74LS138 chip. 74LS138 is a 3 to 8 decoder. What that means is there's 3 input lines here, and depending on what they're set to, one of these output lines will go low and the rest will be high. So that will allow you to select a device based on these 3 inputs. Now there's 8 combinations. 2 to the power of 3 gives you 8 combos there. So essentially the gimme can choose any of 8 devices, and that will cause the outputs here to update. If we look at where those outputs go, one of the output is to SCS bar, and the bar at the top means it is active low. CTS bar here, very good drawing there. CTS, so the cartridge select bar. ROM, which is another signal I'll talk about in a second. And then there's this line here, which actually goes off to the PIAs. So here's one of the PIAs, and then goes up here to the other PIA. And then there's a bunch of unused connections on there, which, theoretically, if the gimme could be reprogrammed, you could maybe add more devices. Who knows? Okay. So the gimme basically says, based on the memory location that is being read or written to, it is going to activate specific outputs here. So the descriptions that we had in the service manual said FF40 through FF5F for SCS. So the gimme, it's controlling, it's mapping memory access. So when it sees an FF40 on the address lines, on its internal addressing, it will make the combination of S0, S1, and S2 such that SCS will become active. Likewise, CTS, this is when it is reading only from C000 to, I believe it was DFFF, right, DF, that handwriting, eh? DFFF. If the gimme knows that the system is trying to read from those memory locations, it's going to set up these output lines. This chip is going to convert that into one signal, which will be the CTS signal. So this CTS signal is then going to go to the cartridge port, the cartridge, and activate the ROM chip on the cartridge so that that ROM chip memory is available for access by the CPU. The ROM signal, ROM enable, this doesn't go to the ROM port or the cartridge port. This actually goes to the ROM chip on the board itself. So this ROM signal, I'm going to just scroll over here to the main system ROM. If you look here on the ROM chip, there is this input. Let's go turn the pen on here. This ROM signal is going to CE bar, which is basically chip enable for the ROM chip. So like I was describing earlier, these signals are basically just going to one line on a chip, which activates that chip. And now if you activate this chip and you've applied power, it is going to output on the data lines whatever data corresponds to the address, the 16 address lines there. So it wakes it up. And a cartridge, like a game cartridge, is basically exactly the same thing. The CTS line will be active instead, which goes to the chip enable, which then goes and outputs the data, whatever's on the address lines it'll output the data to. So let's go back a bit here. Let's take a look at the SLENB signal. So basically this is the internal device selection signal that we talked about earlier. It comes from the cartridge port, so it comes from your external device, and it's got a bar above it, which means it's active low. So SLENB will be active when your external device pulls this line low. It goes into the 74LS138 and it goes into line G1. Now G1, G2A, and G2B are the enable lines for the 74LS138. This chip, you know, unlike some others, instead of just having one enable line, it's actually got 3 of them. G1 is active high, G2A and G2B are active low. Okay, so this here signal, the combination of them, this one needs to be high, these two need to be low. If we look at the overall circuit, these 2 lines are actually forced low because they're tied directly to ground, so those are fine. Those will always be active in the circuit. And then this line here, plus 5 volts, goes via a resistor to the SLENB line, and it forces it high. So this one will also always be active, except when the external device specifically pulls SLENB down. So if the device pulls it down, then this chip goes inactive. Okay, well, what happens when that chip goes inactive? What's going to happen is that SCS won't be active. None of these lines will be active. So SCS won't be active. CTS won't be active. So your hardware, external hardware, is going to be deactivated. Your cartridge will be deactivated. Your internal ROM will be deactivated, as well as your 2 peripheral interface adapters, PIAs, which are on this line, and they're basically connected. There's 2 chips on, one down here and one up above. The PIAs are, you know, all your internal devices, so your keyboard, your serial port, all that great stuff is all connected in through the PIAs. What this does is this disables all the hardware in the system, and it allows you, if you have an external device, to essentially take over the computer. And you know, you could write directly to memory, for example, if you wanted to do a DMA disk controller, or if you wanted to read directly from memory and do some great stuff with like a VGA adapter or something like that. You could use theoretically the SLENB line to take everything over and do that. Part of the fun of having a home lab is that sometimes you've got a few tools you can use in order to test a problem out. And in this case, I'm going to use my trusty HP 5245 counter, and the main reason is because it's the prettiest. So what I'll do is I'll take the leads from the counter, and I'm going to connect these up to the SCS lines, and we'll see what the Coco does when I power it up, and we'll just see how many pulses there are on SCS. The gimme chip is right here, and right next to it is that 74LS138 3 to 8 decoder. So what I'm going to do is I'm going to take my probe ends and I'm going to pop one of them on the SCS line there, and then I'm going to pop the other one onto a nice ground point. Find one here I can easily clip onto. I think that looks pretty good, and we'll start the machine up, see what happens. So Coco's all connected up to the counter. I've got the SCS line up there, and let's power it up, and nothing happens. Now the SCS is the spare chip select for the cartridge, so it actually kind of makes sense that we didn't get any counts on the counter. Let's try again when I plug in a cartridge, and we'll see what happens. Turn that off, my trusty Coco SDC, and we should be able to see this thing boot up, and there we go, and there we go, 35907. So it actually triggered that SCS line, well, 35,907 times as it was reading memory. And you know, I don't know what to take from that, how many times it read or whatnot. It doesn't seem to be a nice power of 2 or anything, but then again, it's cycling through the code and triggering that line high and low as needed. So, kind of interesting. Let's try the CTS line and see what we get. Okay, so we had it on the SCS line there. Now let's put it on the CTS line. Clip that around there. And I think we're good. Let's see what we get. Okay, here's the CTS line. Let's power up the Coco. And 2 triggers of the CTS. So it almost seems like it's looking for the cartridge, not finding it, and giving up. Let's do this again. Power it up. Now it's at 4. Interesting. Okay, I'm going to plug that cartridge in. We'll see what happens then. Cartridge is in, and go. And there we go. Every ROM read on that cartridge was triggered on the counter as it powered up. Try that again. And there we go. 869,000 reads, presumably, of the cartridge ROM. We could see from the previous test that the SCS and the CTS lines, go crazy when there's a cartridge in the slot. But I want to show you programmatically how you can trigger those lines or how they work. The way I'm going to do it is I'm going to use another toy, which is the logic analyzer, and I'll use this little breakout board that I made. It's not beautiful, but this allows me to plug into the cartridge slot of the Coco, and I can see the address lines and the data lines on the Coco itself, so I can basically monitor what's going on. So let's plug this in and see how we can trigger the SCS line. I set up the logic analyzer to trigger on FF40, so when it sees on the address line FF40, it will trigger and it will show us the results. So we press run, fire up the Coco, and I'm going to enter in a quick program, print peak and HFF40, and there we go, it triggered. Address FF40, data's got 7E on it, and SCS is low temporarily there, and it goes back to high. So you can see when I access that address, that physical data line went low. So it's a direct correlation between reading or writing to those addresses. Well, I hope you enjoyed this video, and I hope you learned something while watching it. As always, leave your comments in the comment section below, and if you like what I'm doing here, please subscribe. Need the subscribers, love the subscribers, and yeah, hope you'll come and watch my channel again. Thanks for watching.